So let me share the lecture slides with you and then we will start. Anyone has any specific doubt? Or let's begin the lecture and then probably if something comes in your mind, then you can clear your doubt. So you have class, Ayush, after this? When all you have?
Yes, sir. We
Okay.
have a class from 4.
I will stop the lecture at 3:55. Perfect. Okay, so let me share the slide. So what I can do, screen share, desktop window, application window. So fine. So Mega slide is visible? Okay, perfect.
Yes,
So
sir.
yeah, perfect. So if you guys remember, we were discussing about, we discussed what is heat, the old notion of heat, which was wrong, and then the current formal definition of heat. Okay, so we said that any energy transfer will be called heat across the system boundary if it takes place due to the temperature difference. Otherwise, it will be work. And we have seen some examples also. So we are again going to recall it. There were some doubts also uh, among you guys that let's say the work done in a free expansion, all such stuff. So we'll take a look of those things. And I think Bhavna or someone has made a very good point that the piston should be massless. But even if piston has mass, if you have checked your email, in the last email, I said that how a work done can be zero, okay, in a free expansion, even if you have a piston with mass, depending on what, if you choose it in your system, then that thing, the effect of mass of that piston will appear as energy and not as work done. So as you got that email, right? And that email makes sense? Ayush?
No,
Bhavna?
sir. No,
Okay,
sir.
perfect, fine, fine. No, or yes, sorry, I mean,
No, sir.
you didn't get the email?
No, sir. I don't know. matlab.
Bhavna, you got the email? Anyone?
Yes, sir, we did receive the email.
Oh, I don't
Yes,
know
sir, we
then why
got.
I
Yes, sir,
didn't
we
get it.
received the email.
Yeah, maybe
The
he missed it.
probably the registration process. I
Oh,
guess.
okay, maybe. Those who are registering late, probably you may miss it. Okay, fine. You can ask your friends. I made a clarification because
Yes, sir.
there was a very good point made by Bhavna, so I thought I should add on this. Okay. Yeah, so we were looking for this heat interaction, work interaction. We have seen that there is something called mechanical work, and then we divided in two parts. There is something called boundary work or boundary movement work, where boundary is moving. Okay, and then we have seen different examples: spring work, surface tension work, work done in extending elastic solid. Then we have seen shaft work. Then we went to non-mechanical work like electrical work, magnetic work. And then after that, we discussed that whether something is heat or work, if it is confusing, then you have to see that what system you have chosen. Depending on what is the choice of the system, an interaction can be heat, otherwise it can be work also. Okay, so we have discussed, I think we spent five minutes on this. Someone from student side raised a doubt also, and then I try to convince you. Okay. Remember that if you are not comfortable with this definition of work, say it thermodynamic work. I am going to add more on this, some more clarification on this. Okay, that many, I mean, especially when I was discussing this example, which you see here, where I said that, let's go to this slide, I guess, this slide, where I said that if you take this heating element inside your system, means if your system boundary envelops this or this heating element also, in that case it becomes electrical work. On the other hand, if you take only the gas in this electric oven as a system, and if you exclude this heating element from your system, then since the heating element has higher temperature as compared to the your system, it's a temperature difference. So we'll call it here on the right hand side heat interaction. Then someone made a very good comment, sir, what's the significance? So as I told you, there is no significance. When you try to formalize things, you have to follow some proper rules. Like here we are following a proper definition of what is work interaction and what is heat interaction. Okay. So if something is not heat, it becomes work. For example, this electrical heating element. If you include this heating element in your system boundary, it's no more heat, it becomes work. And only to convince you, I said that since electrons are passing your system boundary, we can say it work because something is moving. But remember that these things may not make much sense for you, and it's fine because as an engineer, we are looking for the final numbers. Whether you include it in a heat or as work, ultimately it's the supply of energy. So don't worry. Okay. But it's my duty to tell you the formal definitions. So that's why I said it with you. Okay. Okay, let's go back. I have something more to tell. Okay, so heat and work depends on the choice of the system. Okay. And the best way is that don't think from work point of view, whether it is work or not. Think from heat point of view, whether it is heat interaction or not. If it is not heat interaction, without any doubt, you say it work interaction, whether you are convinced or not. In the framework of this thermodynamics, which we are studying, you may think differently. That's fine. No one is stopping you. No one is stopping you. But if you talk about the framework which we are going to follow, the formal course of thermodynamics, if you think it is not heat, means if there is if the energy transfer is not due to temperature difference, without thinking anything, you say it work. That's all I can say. Okay. So if I conclude, let's say after so many slides, if I have to conclude something, I will conclude this way: that heat or work, both are energy in transit. That I already emphasized in last 2 lectures. And once, so remember, these are boundary phenomena. So these transfer takes place at the boundary, the system boundary. And once this energy transfer or this form of energy, heat and work, or energy in transit, let's say, when they cross the system boundary, after crossing the boundary, they disappear and become the part of the energy of the system, which we call capital E. Okay, so I think this makes sense. So you cannot say that you can accumulate work. Or can we define work for a state? Let me see whom I can interact. So Abhilas, hello, Abhilas.
Yes, sir.
So Abhilas, do you think so? You know what is state, right?
Yes, sir.
So a state is like a state is defined with the state variables, which are actually properties of the system, right?
Yes,
for
sir.
example, in thermodynamics, is thermodynamic properties of the system. So do you think we can
Yes,
define work for a state?
Work
What
for a
are
state.
what are your thoughts? Yes, no, whatever you think.
Sir, in a particular state, if there is no change occurring, how can there be any work done?
No. Again, I'm saying you have to say yes or no. Can we define work for a state? Anyone else? If you want to add what
No,
Abhilas is
sir.
saying. No. See,
No,
I
sir.
have written, yeah, good. See, heat and work are energy in transit. So you cannot define it for a state. If you go from one state to another state, there will be heat and work interaction. And then this will disappear. Disappear means it will get added to the energy of the system. So you can define energy for a state, not heat and work. So never get confused. State contains energy. Energy is a property. You cannot define heat and work for a state. Okay, perfect. Abhilas, it makes sense for you?
Yes, sir. Absolutely. That's fine.
Now, there is a lot of confusion always, and I'm sure from J time itself, probably sometimes we mug up this thing that thermodynamic work, or in fact work, PV work, done in free expansion is 0. And I know that it's really confusing. Okay, I'll tell you why it is confusing, and still there is no certain answer for this. There is in thermodynamics sense, I can convince you why work done in free expansion is 0. See, one can always argue that if there is a force and if there is a displacement, then from a mechanical engineering point of view or mechanics which we studied earlier in our school day, it says that force into displacement, it should be some work, right? So why we say that thermodynamic work done in free expansion is 0? Now see what picture we have generally in our mind, that we have a piston fitted with a cylinder, and then this piston is moving against nothing, against vacuum. So there is a gas inside the piston and piston is moving against vacuum. So if we think from mechanics point of view, there should be some work done because there is a force applied by gas and then there is a displacement. But the example which we are picking or which we are discussing, that is not the correct example to understand the free expansion. Free expansion using a piston is not possible. So I am going to give you the more accurate example, and then probably I can convince you why we say thermodynamic work done in free expansion is 0. So never try to quote that piston cylinder example for free expansion. Maybe you have solved some problem during your JEE preparation, or maybe you will see some problems in some books where they say that there is a piston and there is a cylinder and then it's freely expanding against vacuum. That problem itself is wrong. That process is not possible. That is not free expansion. So what is actually free expansion? That I am going to see, and probably then I can convince you that that's why work done is 0 and we are not violating any principle of mechanics. Okay, let's see. See, this is the example how free expansion takes place. What happens that you see in the left hand side, there is a gas trapped in a chamber. So there is a stopper, a solid partition you can see. And as soon as you remove this solid partition, gas freely expands. So what is happening here? So this is the correct example of free expansion, not the piston and cylinder system. That is not possible in real life. So as soon as you remove the partition, there is no system boundary. Your gas molecules are pushing nothing. Okay, there is no system boundary, nothing is moving. Fine. So in that sense, we say that work done is 0. So if work done is 0, then how we can understand this phenomena? So that we will see that it is this can be understood in terms of entropy generation. That we'll see when we'll cover the second law. That actually this free expansion process where we say work done is 0, because you are not pushing anything. You are not pushing even a piston. You just remove the partition and then gas expands in throughout this volume. Okay, this we can understand in terms of entropy generation, that we'll see. So you have to wait. Remember, it is an irreversible process. The way you define f dx integral, force displacement integral, or p dv integral, that is for a reversible process. More specifically, quasi-static process that we will see. Because reversible process is not possible in real life. Soon we will see. What is possible is quasi-static or quasi-equilibrium process. And this is not a quasi-equilibrium process. And I will, if you are not getting this point quasi-equilibrium, wait for a few minutes, and then you will see. So this is irreversible process. We will discuss what is reversible, irreversible. You cannot. Well, it will be very wrong to say that we cannot retain the system to the original position. Yes, we can. You put a what we call partition at the top, and then try to compress the gas. You retain back the original configuration of the system, but that is not reversible process. Definitions say that reversible process means both system and surrounding can be restored. This statement may sound difficult for you right now. What I mean by system and surrounding both should be restored, that will be clear when we move to the future slides, especially when we see the heat interaction under second law. Okay. Because the definition of reversibility or reversible work, reversible irreversible process, it's not that whether we can get back to the original configuration of the system or not. It is something else, more deep, that we will see. So remember, free expansion is an irreversible process, And frankly speaking, for irreversible process, finding work done, it's very difficult in general. Okay. However, for this special case of free expansion, there is no work done because you are not pushing any system boundary. I mean, there is no boundary. Okay. I mean, system boundary, one can always draw a system boundary and you can say that, let's say I'm pushing. But you have to see it from practical point of view that you remove the partition and gas just freely expands. So this is the correct example of free expansion, and here we say work done is 0. Okay, so I thought I should quote the correct example to explain you free expansion, work done in free expansion. So we are not violating any principle of mechanics. Okay, in mechanics there is a force and there is a point of application. Here there is no point of application. Where you are applying the force? Nowhere. There is nothing on which you will apply the force. As soon as you remove the partition, there is nothing. It's vacuum. So there is no point of application. Where you are applying the force? If you ask the question to yourself, at what point you are applying the force? There is vacuum. You can't apply the force at all. Okay. So that's all from my side. Still, one can argue, and probably I won't be able to convince you. Now it depends on you how much you are comfortable with this framework of thermodynamics. But I think this much discussion is sufficient from my side. Any comment? Anyone still thinks differently? Or it's fine? Anyone? It's fine? Anyone just say yes, I will move. It's fine?
Yes.
Okay, let's go ahead. Okay, I have included some example to explain you that what does it mean by E, because you remember, just to recall, that in energy we said it includes K, P, U and others. K is macroscopic kinetic energy, P is potential energy, it can be gravitational, elastic, anything, and U includes the microscopic or molecular kinetic energy, that's what we said, and others include chemical energy and nuclear energy. In some books you will find that the others is also included in U. Okay, so that's just a matter of convention, that what convention you want to follow. Okay. So just to give you an example, you see, this is an example of burning of a candle in an insulated room. If you consider this whole room as your system, which includes this candle, okay, then of course there is no expansion, it's a constant volume. So volume is constant, so W is 0. Okay, there is an insulation around the room, so Q is also 0. So delta U is also 0. Anyone has anyone disagree with this? And then we can discuss. Let's see. That delta U is 0. I can confuse you. Let me confuse you. Since we are burning a candle, and since heat is getting transferred from this candle to the air molecules inside the room, the average kinetic energy of the molecule will increase. So don't you think internal energy should increase? And if not, can anyone answer that? Oh, sure. Sorry. Rather than wait, let me put this way, that it's not U. Sorry, it's E. But by mistake I'm writing. You know that how we have defined E. Okay. By mistake I'm writing E is our total energy of the system. So W is 0, Q is 0. So delta E is 0. Okay. According to first law. Anyway, we revisit the first law. But this you know from your school education. So what do you think? That don't you think that this and hint is there, so you can answer. I am trying to confuse you by saying that since heat is getting transferred from the flame of candle to the surrounding, so the energy of the air molecules will increase. So can you clarify?
But the energy of the air molecules might increase, but as a whole, like the energy is only getting transferred. There's no increase in energy.
Yes, true.
Delta will remain
Chemical
yeah,
energy.
That's it. So yeah, perfect. So that I have written. Yes. So energy, as I said, it includes others. Others is that chemical energy plus this U, average kinetic energy. So although the average kinetic energy of the trapped molecules are increasing, but that is at the cost of chemical energy, and chemical energy also the part of total energy. So that's why delta H zero. Okay, so that's a good example to get the feel of what E consists of. E consists of chemical energy, what you know as U, that is average kinetic energy of trapped molecules, and so on. Anyone has any doubt, because two students already answered, so I can assume almost everyone got it. If anyone has any doubt at this point, I mean in this example, feel free to ask me. Okay, fine. This we already discussed. Okay. So, so today we are going to see the first law from Joule's experiment point of view, because see, it's very important that we should understand that how these laws are established. Okay, because before this you just use this law without giving thought that, I mean, why it came in picture and whether it was obvious or not when it got discovered. Today you may think it's very obvious, but it may not be. Okay. Okay, so what Joule did, so Joule did this experiment in 1848. I may be wrong also, 1840, whatever, doesn't matter, but a rough timeline. Okay, and his experiment was as I am going to describe. So as you can see, there is, when there is 355, just remind me, okay, so that I can stop the class first time. Oh, we have enough time. Okay, so as you can see, there is a chamber, closed chamber, filled with fluid, and there is a mechanical sphere. Okay. By the way, my cursor is visible when I move this cursor?
Yes, sir.
Okay, fine. So there is a turbine, not turbine, you can say mechanical sphere. And the top part of this, you can say pulley or something like this. So it is connected with a mass. Okay, fine. And let's say you put certain number of wraps here on this pulley, means multiple time of wrapping. Okay. So what will happen? So this was a Joule experiment. When this will fall, this mass m will fall downwards due to gravity. This pulley will rotate and hence mechanical sphere will rotate. And due to this steering, what we expect? What will happen? Or think from Joule points of view, what you observe. So there is a temperature increase, and that Joule's noted down using this thermometer. Okay, fine. So what was his first step of experiment? That he noted down that how much this mass has fallen down. Okay, so this way he know the work done. Of course. Wait for a moment. So that way he knows that how much work has been done on the fluid, which is simply the decrease in gravitational potential energy that I have denoted by delta W. Okay. So system is going from 1 to 2 on the right hand side. System is going from 1 to 2, and what is happening? Temperature is increasing. So one temperature, lower temperature, system goes to higher temperature, and there is a work input. So through path A. Okay. This experiment seems very easy. Can anyone comment why it was not? I mean, even today it's not an easy experiment. Can anyone think?
Sir, I think the insulation part.
Insulation part, friction. You know,
Yes,
to ignoring the
friction
friction at the pulley and all this, it's not easy. It seems very easy, but see, if you say that only the decrease in gravitational potential energy will work, then all other components you have to, all other losses you have to get rid of. At least that should be ignorable, very, very minimal, right? So that's why this experiment was not easy. That is point number one. Point number two, why Joule, we appreciate Joule so much, and the energy, I mean the SI unit of energy Joule, in honor of Joule. The reason was that, you remember, I have shown you the statement that people were believing before Joule that heat is an invisible odorless fluid which transfer from hot body to cold body. It cannot be destroyed, it cannot be created. And he has to, what Joule showed, that it's wrong. It's nothing but a form of energy. Before that, people were thinking it's an invisible fluid, kind of matter. You know, the way we say today antimatter, people are thinking there is some matter which is invisible and which flows from hot to cold body. Whereas what Joule did, he showed that no, simply by doing work you can convert it into heat. So you can generate heat at the by spending work. At the cost of work, you can generate heat. So he was the one who showed first time that this conversion is possible. By doing work, I can create heat, and hence this statement is wrong that heat is a invisible fluid which flows from hotter to colder water. Here we are simply steering this. There is no temperature difference, and we are creating heat. According to the earlier definition, heat only flows. It cannot be generated. Whereas here we are generating heat. So that's why we appreciate Joule so much, and we have given him honor by saying that the SI unit of energy is Joule. Okay, but before that, of course, before saying that the energy unit is Joule, there was a committee, and then that committee decided that in the honor of Joule we should say Joule. But before that decision, that equivalence was not there. That unit of energy, heat is also Joule, unit of work is also Joule. That was not established. And since it was not established, this gave rise to Joule equivalent, which we are going to see. Anyway, let's come back to the experiment. So what was the first step of experiment? That Joule was knowing that how much that mass is falling. And once you know how much mass is falling, he can calculate delta W. So delta W will be, why delta W will be simply decreasing gravitational potential energy, mgz. Can anyone say why I have put this delta sign in a different way? It's not D. Anyone? Any comment? If not, then you have to wait. If yes, let's see if someone has some comment.
Because we are considering only infinitesimal change.
Then I can put small d also. Why this sign delta?
Because it is a path function, we cannot.
Yes, it is a path function, and for a path function, you cannot define an exact differential. So we'll come to this. So I thought whenever there is some doubt, I should raise it so that I can clarify it later. Okay. So few people know. Those who don't know, wait. Okay. So we know delta. So Joule was knowing what is delta W. Then what he did? He measured dou Q. I mean Q. How we can measure Q? By the way, follow me. How we can measure Q? Or how Joule measured Q? Just think from Joule's point of view.
Change in temperature.
Change in temperature. So how we calculate change in temperature? Then how we calculate Q? I mean dou Q. Anyone?
MCP delta.
MCP delta. Perfect.
Yes.
MCP delta. Yes.
Sir,
And-
I was
Yeah, please. Yes.
Sir, I was thinking that as we are using a pulley in this mechanical process,
Yeah.
wouldn't there be frictional losses at the pulley too?
That's what I say that the only the one thing for appreciating Joule so much is that in 1840s he somehow managed to minimize these losses. Who is it?
Devesh.
Devesh. So that was the beauty of his experiment. It's not easy. You are right, and you cannot get rid of it completely, but at least up to a very large extent you can minimize it. Okay. Have I answered your question?
Yes, sir.
Yeah, and remember today it's possible because due to this advanced machining technique. But in 1840s, it was not so easy to get a pulley with very less friction and all such stuff. What you were thinking. So that was also a very important point at that time. Anyway, Acha. So someone answered that MCP delta T. So before Joule, what was the unit of heat? Anyone?
Calorie.
Calorie. So Joule measured it in calorie. Remember, work done. Yeah, is so today we know work done in Joule. But let's say when Joule was doing the experiment, probably he has defined work done in Newton meter, force into displacement. Okay, that is the unit of energy. So on the left hand side, he had Newton meter. Okay, on the right hand side, so he measured work done by this MGZ, say 8 Newton meter, because you assume that you are Joule and you are doing the experiment, and when you are Joule, there is no unit of Joule. Okay, because after you there will be unit of Joule. So before Joule, on the left hand side, the work done when you calculated, its unit is Newton meter. And on the right hand side, when you calculate dou Q by measuring the temperature change using thermometer, you know the mass of the fluid, so mCp delta T or mc delta T, you find out dou Q. And since one is in Newton meter and one is in calorie, so if you wanted to establish this equivalence, you have to put an equivalent number, and that you know as Joule. And that's why I think 1 Joule is 1 calorie is 4.18 Joule, right? Or other way. I don't remember. Anyone comment?
1 calorie is 4.
Yeah. So from there it came in picture. Okay. So before establishing this unit of work or energy will be Joule, since heat energy unit was calorie, work unit was Newton meter. So in order to establish this equivalence, this Joule equivalent came in picture. So remember, it's nothing but converting the calorie into Newton meter, right? And the Newton meter, formally, let's say there was a committee who decided rather than saying Newton meter, because it's a thermodynamically difficult process, you need a lot of energy, a lot of breathing in saying Newton meter. So let's say Joule. Anyway, I'm just kidding. In the honor of Joule, people decide. I mean, a committee decided, international committee on units and there's something else, units and some dimension units, whatever it is. They decided that formal unit of work of any energy will be Joule. Otherwise, before that, in order to convert calorie into Newton meter, you have to multiply it with this Joule equivalent. Okay. So that was the overall, the Joule's experiment. Huh? Okay. Another thing which I wanted to share is as follows. I think the second, before this I should tell you, just give me a moment. So we'll come to that part later. Huh? Okay. So this was the Joule experiment, and he established this heat work equivalence. Okay. That's why we appreciate him a lot. Right. So you can remember that what was Joule's contribution? Energy heat equivalence. Before that, heat was not the form of energy. That's what people were believing. Okay. Now we can extend Joule's experiment for any process. Okay. But before that, we have to go to a cyclic process. So before we go to the next slide, just read this experiment, this statement, that there exists for every thermodynamic system a property called energy, and the change of energy of a system is proportional to the mechanical work done on the system in an adiabatic process. This was the statement made by Joule. You know why? Because there is an insulation in the Joule's chamber. You see, otherwise heat will go to the surrounding. And well, that was not the idea of Joule. What Joule did, that he wanted to know that only fluid temperature should increase. So he had put the insulation. So it's an adiabatic process because there is no heat transfer, right? Out in the surrounding. Fine. So if there is no, okay, just a moment. We missed something here. You know what? I don't know whether someone has noticed or not. Let's see. Achha, how I am defining delta Q for what we say this. How we are defining this Q for this fluid? Don't you think there is something wrong? I also overlooked this issue, and then I will correct it. Can you see the system boundary? So system boundary is this insulation, right? and you are doing some work, fine, using this software, means that's what Joule did. Huh? So, do you think there is any heat interaction across this boundary? Anyone? And I'll tell you that I just overlooked it. I was thinking something else. And do you think there is any heat interaction across the boundary?
Viscosity?
No. Forget about those things. Huh? We are ignoring all those losses. I'm saying, do you think there is any heat interaction across the system boundary? The system boundary is this chamber.
In the thermometer?
Sorry?
Across the shaft.
No, thermometer is just a probe to measure. So don't get confused with that.
At
Maybe
the upper, at
What
the
is-
junction,
Sorry?
The shaft.
the rotating paddle and the
No, that is
interface
work
with the
interaction. That is work interaction, right? I am talking about, is there any heat interaction? You remember, we have, see, this shaft is crossing the boundary. So this is shaft work. So work is fine. That we all get convinced. You remember this?
so
is
the
shaft,
temperature
sorry,
difference between the fluid and the rotating.
No.
Shaft.
Who said you? No. I mean, that this is, I don't think that this is correct. Why this mechanical stirrer has higher temperature than fluid? No. That's what we discussed. That we are creating heat at the expenditure of work. There is no temperature difference. You need a temperature difference to define heat across the system boundary. But that doesn't mean that in order to create heat, you need the temperature difference.
But sir, let's say that the outside,
Yes.
the temperature of this universe, like the outside temperature, is not equal to the system temperature. And
Which
the
outside
rotating part,
temperature?
just outside the insulating surface.
Achha, outside the insulation. Okay. Yes. Fine.
It is not equal to the temperature of the fluid.
Okay.
Then
Doesn't matter.
the
It's
rotating
insulation.
part will conduct heat.
No, why its paddle will conduct heat? I am not getting your point. See, we are just rotating the fluid by this paddle. I will make this paddle also insulating at the top. From where the heat will be lost by conduction.
Okay, so I did not consider that the paddle is
Oh,
insulated.
no. See, means when I say adiabatic, there is no heat transfer across this system boundary. You have to ignore those pulley and all this.
Sir,
part.
Sir, is the heat due to the increase in kinetic energy of the water molecule, means the fluid molecule?
That's what I'm asking. Do you think there is heat interaction? First say yes or no. I want an answer from anyone.
No, sir.
No, there is no heat interaction. And I also made that mistake because I overlooked this thing. I'll explain you why. We just discussed where there is no heat interaction. So then where this, yes?
Sir, are you talking about
Sir.
the fluid's specific heat capacity?
You can say heat capacity. And that will be considered as the energy of the system, MCPT, right? Are you getting my point? Hello?
Yes. Yes,
Yeah.
sir.
So listen carefully what I am saying. And then I want your comments. See, first let me give the statements and then you comment. So let's see. What I am saying, there is no heat interaction. Ignore the heat losses through this top part of the pulley or this stirrer. Okay, there is no heat loss. There is no heat interaction across this chamber. So delta Q is 0 from going from 1 to 2. Listen carefully. Delta Q from going from 1 to 2, I am saying, means 1 to 2 means the process is that this mass is falling and there is some temperature change inside this chamber. So that is going from 1 to 2. And from 1 to 2, there is only work interaction. There is no heat interaction. So what this work will do? This will increase the energy of the system. What my system contains? Fluid. And for a fluid, like liquid, how we define the average kinetic energy in terms of MCPT. Okay. That's what we know as, capacity, heat capacity, specific heat capacity, and then you multiply it with M. So you can say heat content. But whatever you say, whether it heats, I will say thermal energy. Many people say it heat content and you may get confused, it is heat. Don't say it heat content, say it thermal energy. Ultimately, what it is the kinetic energy of the fluid particles. So now I am concluding it. that there is work interaction across the system boundary, which is my insulated chamber, but there is no heat interaction. So this whatever work we are doing, it is increasing the average kinetic energy of the fluid molecules, and hence whatever we are doing work, that will get added as E. It will add energy to the system. Anyone has any comment on this? You think anything wrong? Then we can discuss. So delta W, till now what we know, delta W, okay, and this is from 1 to 2. Okay, and so what Joule measures? Listen carefully. What Joule measures from going 1 to 2? Only delta W. And what he was knowing, that what is the temperature change. Till Joule, there was no first law. So people were not knowing E. Remember, 3 statements. When Joule did this experiment, going from 1 to 2, what was happening? This mass was following by a distance Z. So Joule was knowing what is delta W. That is mgz. What else he was knowing? The initial temperature and the final temperature. He was not knowing the definition of energy. In order to convince, since today we know what is energy. Energy is the property of the system. That work done by this displacement due to which this pulley, this steer rotates, that will increase the average kinetic energy of this fluid molecule, and that will appear as change in E, capital E. Up to this point, anyone has any confusion, or you disagree with me?
Sir,
Yes.
like sir, if the mass m is going down by dz, then the work would be like mg dz.
Yeah, mgz you say. Why dz? Z. Fine. Okay.
So sir, that amount of work is getting transferred into the rotational
rotational motion of the sphere.
rotor.
Okay. Yes. And then it's getting transferred to fluid. Right.
But sir, how can we say that it is completely transferring? It is like both of them are having energy.
Who is it? Who is it? Tell me the name.
Ayush.
Ayush, we are discussing this experiment in a very flexible condition. Whether it is getting complete transfer or not, that is not our agenda.
Means sir, what I want to say is that
you have to assume it. You have to make this assumption that those, it's almost getting transferred. There is no loss. Almost there is no loss. Whatever that rotational kinetic energy of this steerer, that is getting transferred to fluid. Don't go into those details that there is frictional losses. We are not.
No, sir, I'm not saying about the frictional losses. What I want to say is that if you are rotating a fan and the molecules nearby, it is getting the that fan is transferring the energy to the molecule.
Yeah.
Then we can't say that the fan is completely transferring its energy to the.
I am saying no, you can't say that. See, that's the experimental bottleneck or experimental limitation, right? That probably Joule also faced. I am not worried about that. Let's say there is let's say there is no complete transfer. That's also fine. Okay. I am saying something different. I am saying, okay, I agree with you that delta W is not getting completely transferred. Let it be. Okay. Some part of, I'll put some eta, some fraction, right?
Sure.
That is fine. I am asking something else. Point number 1, you answer. Do you think there is any heat interaction across the chamber?
No, sir.
No. Okay, so that you agree. If there is no heat interaction, where this work is going? Even if the incompletely or partially,
work is transferring energy to the chamber.
So energy to the chamber. That's what I'm saying. It may not be complete. So your point is also right. But
that the temperature which you are noting, it will not give you the exact work transfer.
No, so I never said that. Okay. See, we have only discussed. Wait. Control X. Let me put somewhere else this thing, and then Control V. I'll put it. I'll hide it. I know why you guys are getting confused. I'll put it later. Let's wait for some time, because this is my fault that I overlooked this. And yes, Ayush. Now you can see only delta W, right?
Yes, sir.
if I go with your comment, with your suggestion, I'll put some eta, so that partial transfer of energy, right? Fine.
Yes, sir.
So that we know, right? So mgh into eta, that you agree?
Yes, sir.
That's it. Step from 1 to 2, that's what all Joule was doing. Fine? Clear?
Yes, sir.
Now what you were saying, that how we know that, what was your comment? This, we haven't calculated delta Q. Okay?
No, sir. Okay. Okay, sir.
That's what your point was, na? That MCP, how do you know that these two are
Yes, sir.
equivalent?
Means my point was that if we are doing some work on the, actually we are doing some work,
Yeah.
that work is getting transferred into the container
True. Container, rather than container,
fluid.
because it's
So
an insulated one.
the point I want to mention was the fan is also rotating, and we
Yeah.
can't say if the molecule, if it is transferring the energy
Okay. I got your point. Now I see your point. You are saying that since this rotator has also some mass, so it will
keep on rotating.
Fine. Okay, that's fine. Okay. So let's say there is some partial transfer. Why it will keep on rotating, by the way? If I stop the mass at height z, why it will keep on rotating?
Sir, if it is,
you are saying that if you ignore all the frictional losses and everything, of course fluid will also get the energy, but this
fluid
will
will
also keep on rotating for
fluid will
infinite
also
time.
transfer the energy.
Yeah. So you are saying that it will keep on rotating for infinite time, right?
Yes, sir.
Okay. If there is a catch, since you guys have just started chemical engineering, tell me why this heating takes place.
Sir, actually,
you said the average kinetic energy of the molecule increases, right?
Molecules
Yeah. So
are
basically
colliding with the fan, and they are transferring the energy.
Yes, it is. So if there is a transfer in the energy, right? So somewhere energy has to decrease. See, if you are transferring the energy, Ayush, right? So how this rotor can rotate for infinite time? It has to stop sometime if it is transferring energy, because you are supplying fixed amount of energy, mgz.
Yes, sir.
Let me clarify this to you. I'm just see what is happening. The moment you say you are creating heat rather than thermal energy, it means your liquid is viscous. Okay, and due to this viscosity, viscous liquid, ultimately this rotor will stop. It cannot keep on running. So ultimately there will be a complete transfer of energy from rotor to fluid.
Yes, sir.
Okay, you think this way, that there is a rotor kept inside a fluid. You just rotate it by your hand, by your fingers. Rotate it and then wait. And if your chamber is insulated, what will happen? Eventually that rotor stops. What happens? When you say that there is an increase in thermal energy of the fluid molecules, indirect you are saying that your liquid is viscous. If your liquid is not viscous, it will never get heated. And since there is a viscosity, I think you have done fluid mechanics course.
Yes,
no.
sir.
So there is if your liquid is viscous, then it will apply opposing force on the rotor, and ultimately rotor will stop. It means that the whatever energy we supply to rotor, that will go to fluid. Okay.
Yes, sir.
And since in the future semesters also we are going to meet many times, keep this point in mind, and I'll discuss it in our future semester also. Whenever you see the thermal energy of the fluid is increasing, it means this is called viscous dissipation. Means due to either you say thermal energy of fluid molecules are increasing, or you say liquid is viscous. Both are equivalent statement. If your liquid, gas is different, but if you talk about this something like liquid, then in case of liquid, if your liquid is viscous, then only there is the moment you say viscous, it means if there is some energy to the fluid, it will get passed to the thermal energy of the fluid molecules. And since it is viscous, ultimately rotor will stop. So now you got the point, what I'm saying, that there will be complete transfer of mgz to the fluid molecules. So that is step number 1, going from 1 to 2. Okay.
Yes, sir.
So from 1 to 2, there is work input, and due to this, which we can calculate as mgz, and that is from 1 to 2, and that will add the energy to the system, thermal energy to the system. That is experiment 1. Then we will come from 2 to 1, and then Q will come in the picture. Quickly I will say, and then we will again repeat it. I want to spend some time on this. That's why I'm discussing, in interactive mode, because this is important. Then what Joule did, he removed all these, these accessories, and he removed the insulation also. So what will happen, if we remove the insulation?
So there would be transfer of energy.
Yes. So what he did, he waited till the fluid come back to its original temperature. Assuming that you have kept the fluid temperature equal to the, let's say, atmospheric temperature, ambient temperature. Okay. That's what we expect. That if you remove the chamber, then fluid will come back to the original temperature. Say the original temperature was equal to the ambient temperature. Fine, Arish?
Yes, sir.
So can we calculate this delta Q? So from 2 to 1, what is the process? First define it. So yeah, I have to discuss with you itself, because if I choose a new guy, there is a wastage of time. So from 2 to 1, what is the process? Quickly.
So 2 to 1. Heat to the surroundings.
Yes, very good. Heat to the surrounding. So this is when I say this Q, you remember this dou Q. So he went from 1 to 2, and there was only delta W. Then he come from 2 to 1, where he removed the chamber, this insulation, and then this fluid came back to its original temperature, which was equal to the surrounding temperature, and then he can calculate dou Q, right?
Yes, sir.
Right? So that was from 2 to 1. This time there is heat interaction across the system boundary, because we removed the insulation. And what Joule found, that this delta W is proportional to dou Q. And then in order to remove this proportionality sign, because left hand side Newton meter and right hand side we have calorie, he put this Joule equivalent. So that was the, and so it means, is it a cyclic process, Ayush? Yes.
Yes, sir.
Because system is going to its original temperature. Okay. So basically his experiment was for a cyclic process, where he found that in this cyclic process, delta W is always proportional to dou Q, where delta W is the work input from 1 to 2, because there is only work interaction, and coming from 2 to 1, there is heat interaction only. So we'll start from this slide. If anyone is confused, I want to discuss this slide at least for next class, means this concept of joules. Then after that, it will be very fast. Thank you, guys. I hope you enjoyed. Okay. And others, please feel free to interrupt or discuss. I mean, so it's good that I participates a lot. But then, if everyone participates, I will be more than happy. Okay. Thank you. Enjoy next class. What is the next class, by the way?
The next class is on Wednesday.
No. I'm from 4 to 5. I'm saying.
Okay, it's numerical solutions of
OD and
PD.
OD and PD. That I think from maths department, right?
Yes, sir.
Yeah. Okay, guys. Okay. Fine. Continue. We meet on Wednesday. Huh? Okay. Thanks. Bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.